Welcome to a lesson in linear functions and a constant rate of change. We define a function or a relationship between quantities to be linear if the quantities are related by a constant rate of change. When we take a look back to a previous lesson with the water tank that was being filled by a hose, one of the conditions was that the rate of filling was happening at a constant rate. And what we had done is we had produced a table which related the time elapsed in minutes since the hose was turned on to the height of the water in the tank in inches. Also, as we progressed, we also had built up a graph, the various points, and noticed that a straight line can be drawn through it. In this problem, 2.2, 15.12 was the reference point, and it represented a known measurement in which when 2.2 minutes elapsed, 15.12 inches was the height of the water in a tank. Also, we knew in this problem that 3.6 inches per minute was the constant rate of change. And we had also discussed how we could use a constant rate of change to determine the height of the water in the tank at 7.2 minutes. So as we're taking a look back, let's see how that was accomplished. First of all, we knew that 2.2, 15.12 was the reference point, and we were interested in finding what was the height of the water in the tank when time was 7.2 minutes. So we first figured out the change from 2.2 minutes to 7.2 minutes. So we looked at delta t. It's equal to t current minus t ref. And then t ref represents that starting value from the reference point, and t current represents the time that we're currently interested in looking at. In this case, we take 7.2 minus 2.2, and we get 5. So as you can see over here, there's a graph which represented that change in time of 5 from the reference point. We then wanted to figure out the corresponding change in height of the water, because then we could use that to go from 15.12, use a change in height to figure out what the actual current height of the water in the tank is when the time is 7.2 minutes. So to do that, first of all, we would recall that the change in output is equal to the constant rate of change times the change in input. And in this context, the change in output is represented by delta H, and the change in input was represented by delta T. So delta H is equal to 3.6 times delta T, where 3.6 is the constant rate of change. In this case, the change in T was 5, so change in height is equal to 3.6 times 5, which comes out to be 18. And so we use that information to go further, and so looking at the graph, we have change in height is equal to 18. In the table, we now know we need to change positive 18 from 15.12. To do this, we're trying to figure out that current height, so it's the change in height plus the reference height. And the change in height was 18. The reference height was 15.12. And when we look at it visually, starting from 0, we're getting 15.12. And then we're going to go another 18 to figure out that the current height is going to be 33.12 inches. So looking at that visually, we have 33.12, and that corresponded then to a point of 7.2, 33.18. So that's a little bit of how we use the constant rate of change to find the height associated with the time of 7.2 minutes. Let's see what other patterns we can discover, because right now we're going to take a look back and see if there's a common pattern that it connects all these ways that we found different points along the graph and the table. So as we do it, let's go back and take a look at how we did this when time was 0.5 minutes. So what we're doing is we're figuring out the change from 2.2 to 0.5. So again, starting with delta t is equal to t current minus t ref. In this case, the current time that we're examining is 0.5 minutes, and the reference time was 2.2 minutes, and that was a change in time of negative 1.7. So we were trying to figure out the corresponding change in height. intuitively knew that because the tank was filling, that if we're looking at an earlier time, that would mean the height was less than 15.12. And so first of all, we need to figure out the change in height. So delta H is equal to 3.6 times delta T. And so in this case, delta T is negative 1.7. So 3.6 times negative 1.7 is negative 6.12. So if the time changes by negative 1.7, the height decreases by negative 6.12. And then what we want to do is figure out what that current height is. So we're taking our change in height plus the reference height, which was originally 15.12. So we have a drop height of 6.12, and that's represented by negative 6.12 plus 15.12, and that gave us a current height of 9. So let's see what we can learn from this and compare the two processes. So what we really want to do is summarize the process that's used. There's things that are common to both calculations that we just did. The very first thing we did is we chose a reference point, and we also identified the input value. In this case, 2.2, 15.12 was the reference point, and we had noted that the input value in this situation will be 2.2. The other thing we did is we found the change in input from the reference value. So in both approaches, when we first started out, whether we were trying to figure out the height associated with a time of 7.2, or if we wanted to find the height associated with a time of 0.5, we first figure out what the delta t was. T current minus T ref. And then what we did is we used the constant rate of change to find the change in output, which is meaning to find delta H. We did that in both cases. We knew what the constant rate of change was, and then we used what we knew about the change in time to figure out the change in height. In this case, that change in height is the change in output. And then what we do is we find the current output value by adding the change in the output to the corresponding reference value. That's represented by the equation down at the bottom. And so we took the change in height plus that reference height to figure out what the current height is. And the height in this case represented the output. So let's see how we could then generalize this idea overall. And suppose we wanted to create an equation that finds the height h of the watering tank in inches for any time t in minutes. So the very first thing we're going to do is choose a reference point and identify the input value. Again, we're going to use the same reference point of 2.2, 15.12. The next thing we're going to do is find the change in input from the reference value. So again, that reference input value is 2.2. So let's see what that means. So our delta t is equal to t current minus t ref. Now in this case, the t current is represented by t. We don't know what that value is, but there's some value of t that represents the current time. The reference time is going to be 2.2. So let's put those values in. And so delta t is equal to t minus 2.2. The next stage is to use the constant rate of change to find the change in output. So let's do that. So again, thinking about what we had in previously, the change in h is equal to 3.6 times the change in t, or delta h is equal to 3.6 delta t. In this case, we do know something about the change in time, the change in t, which is equivalent to t minus 2.2. So we're going to replace the delta t with t minus 2.2. And so we're left with delta h is equal to 3.6 times t minus 2.2. Now let's look at the last one, which is to find a current output value by adding the change to the corresponding reference value. So what this is saying is, first of all, let's make sure we remember the reference output. In this case is 15.12. And so the current height is equal to the change in h plus h ref. So h current is equal to delta h plus h ref. Well, let's see, the current h is represented by the height h, so that's the first replacement we're going to make. So h is equal to delta h plus h ref. Now delta h We just found in the previous step that delta H is equal to 3.6 times the quantity, T minus 2.2. So let's replace that. Now let's see, the H reference, that represents the reference height, or the reference output in this case, and then we're looking at that is 15.12. So we'll make another replacement, another substitution, and so H is equal to 3.6 times T minus 2.2 plus 15.12. And there we have an equation. So, looking at this, we have the equation 3 times the quantity, T minus 2.2 plus 15.12. So T minus 2.2 represents the change in input, and 2.2 is our reference input in this situation. We also have 3.6, which represents the constant rate of change, and the constant rate of change times the change in input would represent the change in output, so that 3.6 times the expression T minus 2.2 is the change in output. Then we take the change in output plus 15.12, which was our reference output. That results in the current height of water in the tank. And this is an equation that finds the height h of the water in the tank in inches for any time t in minutes. What we're going to do is now just focus on this equation. So let's take a look at and see how this becomes a useful idea in looking ahead. Imagine that we wanted to create the table just using an equation. Now this equation is supposed to capture the idea of all those calculations that we were doing before, but done as one equation, because it does capture finding the change in input, then finding the CROC, which is the constant rate of change, and finding that change in output, and then adding it to the reference output, which would then determine that height of water in the tank. So let's see how this actually works out and see if it is consistent with our previous findings. So let's begin. Let's say we wanted to use this equation to find the height of the water in the tank when the time is 0.5 minutes. Now we expect the answer to be 9, but let's see if it actually works as we expect. So we're going to put 0.5 in place of t, and then do the math to see what results. So order of operations say we would take 0.5 minus 2.2, and that's going to calculate the change in input. And the order of operations says we would do the multiplication x, we would take 3.6 times negative 1.7, and by doing so, we're going to find the corresponding change in output. And then when we take negative 6.12 plus 15.12, that would actually then find us the actual height of the water in the tank. So we'll do that. That just means doing an addition. And so h is equal to 9, which is really neat because that's exactly what we had found using the earlier process. Okay, let's take a look at another one. Suppose we wanted to find the height of the water in the tank when time is 7.2. Now we do expect an answer to be 33.12, but let's see how this works. First of all, we'll put 7.2 in place of t. Order of operations says we would do 7.2 minus 2.2, which is exactly what's going to calculate the change in input. And so we now have the next part, which is to figure out the change in output, and that is by taking the constant rate of change times 5. And looking at it from an equation perspective, all it is we need to do multiplication before we do addition. So it's working consistently like with how we had found the process for change in output. So we'll do that. So now we have 3.6 times 5 is 18, and then taking the change in output, which is 18 plus 15.12, will give us 33.12, which is exactly the same as we had found earlier. So the equation finds exactly in the same process and the same order the height of water in the tank for any given time in minutes. So this is working great. Let's see what we can do with the remaining values that we had produced in the table. H is equal to 3.6 times t minus 2.2 plus 15.12. Let's put in 1.5 in the place of t, and we're going to do the calculation. So we're going to first do 1.5 minus 2.2. And so now we are going to do next, because multiplication is next, 3.6 times negative 0.17. That's going to calculate the change in output. And now we have the change in output, which is negative 2.52 plus 15.12. That's going to give us the resulting height of water in the tank. And that's 12.6. And notice that's exactly what matches with the table that we have developed earlier. So this equation is working really well. Let's look at one more. Let's see, we're starting with 3.6. H is equal to 3.6 times t minus 2.2 plus 15.12. So we're going to replace t with 5. First thing we're going to do is what's in parentheses, 5 minus 2.2. That gives us the change in input. Then we're going to take the constant rate of change, which is 3.6 times 2.8, which is what the order of operations would also tell us to do, which is to do the multiplication. So that when doing so, we're going to find the change in output. And when we do it, we get 10.08. So what we currently have is h is equal to 10.8 plus 15.12. And 10.08 is representing the change in output. And 15.12 is that reference height. So let's add those together. That should give us the current height of the water in the tank. And that's going to give us 25.2, which is exactly matching with what we had earlier in the table. So the equation correctly reproduces or recreates all the values in the table. So that gives us confidence that this equation is correct and that it correctly models the relationship between time and height of the water in the tank. And notice that it recreates all the points that you see here. Line passes through them. But we also want to see is if 0, 7.2 also is produced by this equation. So let's do that. Okay, so 0, 7.2 represented when we were looking at the initial height of the water in the tank. In other words, when time is 0. So we'll put that in. So time is 0. So that means that the change in input from the reference point 2.2 is negative 2.2. And then our change in output is by taking 3.6 times negative 2.2. Then, okay, now we're looking at the current height of the water tank is the change in output plus that reference output, or that in this case the reference output is reference height of water in the tank. So negative 7.92 plus 15.12 is 7.2. So that is consistent with what we had found. So what we're looking at now is that this equation has reproduced all the values in the table and actually would even reproduce any other values along that line. Just simply find its time. That's reasonable in this situation, and it will calculate the correct height of water in the tank at that given time. It is very powerful. But what we have also learned is we have discovered one form of a linear equation, which is similar to the one above. One form of linear equation is that you could say, for example, for the height of water in any given time, it's going to be the constant rate of change times quantity t minus the reference input plus the reference output. As we look at this, the constant rate of change in our situation was 3.6 inches per minute, but you could imagine that it could be also be the water could be draining or the water could be filling at a faster rate. So this would have worked regardless of what constant rate of change is. The reference input and the reference output are subjective. You might have had a different reference point from which you measured everything else. And it correctly will, t minus reference input will determine the change in input. And when you take the constant rate of change times the change in input, you do get the change in output. And then when you get the change in output plus the reference output, you would be able to determine the height of the water at the tank at any given time. That concludes this lesson. I hope you found this helpful.